Alright, so hello everybody. It's good morning. It's rather gloomy outside. Today let's talk about the stress development in beam problems. Of the last time that we discussed how to construct. So I emphasized you several times that we are not calculating the shear force diagram and the bending moment diagrams. We are constructing, okay? So we are constructing the shear force diagram and the bending moment diagram. The reason that I'm calling the job is construction rather than calculating, the shear force diagram and the bending moment diagram is that we don't have to actually the calculation is really minimized when we try to draw the shear force diagram and bending moment diagram. So once you understand the characteristics of the shear force, change of shear force and change of bending moment, with respect to applied load and then the shear force and the bending moment, then you can easily construct, okay? You can easily construct the shear force diagram and bending moment diagram. And then also the shape of shear force diagram and the bending moment diagram can be determined by the nature or the characteristics of the applied load and the shear force diagram. Now, for instance, if the shear force diagram is constant, then which means the slope of the bending moment diagram is linear, okay? Depending on the sign of the shear force diagram, if the shear force diagram is positive, then the slope in the bending moment diagram is also positive. And if it's negative, then the slope is also negative. The bending moment diagram also has the negative slope. And then let's say the shear force diagram is linear, say linear. Then linear means my bending moment diagram, because the slope of bending moment diagram is determined by the shear force diagram. If the shear force diagram is linear, then my bending moment diagram should be quadratic, okay? So we may have two different quadratic. So whether it is concave upward or concave downward. If concave upward means it must have what? The positive value, and the concave downward is a negative value. That's how we can determine the bending moment diagram. And then let's say if the shear force diagram is linear, at a certain point maybe the shear force value should be, the magnitude is small, and because it's linear, and here the shear force value is greater than the other place, okay? So then, which means the slope in the bending moment diagram should be small. Then the bending moment diagram should be start smoothly at this point, and then the slope increases, okay? So quadratically. That's how we construct the shear force diagram and the bending moment diagram. It is very easy actually. The last time also I provided you some or more examples in addition to the examples given in the textbook to give you, the detailed view regarding the construction of shear force diagram and bending moment diagram. So I hope you enjoyed my video because I have a meeting outside. That's why I uploaded my lecture video for you guys. So do you have any questions before we start today's lecture regarding the shear force diagram and the bending moment diagram? No questions? 수연이, 장수현, do you have any questions? How about 지수, 강지수, 경표는? Alright, so now let's talk about today's subjects. Today we're gonna talk about the stress, okay? The stress in beam problems. Okay, let me revisit the definition of the stress and what I mean internal forces, okay? Say, for example, the shear force. Shear force is nothing but just integration of the shear stress over the cross section. That is the shear force. And then bending moment is integration of the contribution of the normal stress to the bending moment. So that's why we need to calculate small forces, normal stress times dA, and then it should be multiplied with the arm length, okay? The arm length. Then it's gonna be stress, and then the distance from the neutral axis, and then its integration. Okay, so what we can see here, the last time we studied, how to determine the shear force and the bending moment at certain point in the beam axis, okay, at this position. So we were able to some representative values of the internal forces. What I mean, I'm using the word of forces to include the force and then the moment, okay? So please understand. So whenever I say the forces, so I'm talking about the two stops at the same time, the force and moment, okay? In general sense, we call force and moment in the terminology of force. So now we have the information of the shear force and the bending moments. So what we want to today is we'd like to draw a relation between the internal forces and then the stress, okay? Internal force and then stress. That's what we want to do. From the shear force, so I want to draw the information of the shear stress. And then from the moment, so I want to draw the information of the normal stress. That's what we want to do. You understand? Okay? Sorry. So here's the outline for today's lecture. The outline of today's lecture is, so we'd like to develop a relation between the moment and the curvature. That's what we want to do. And then from this relation, we'd like to define so-called flexor formula, so-called in 우리말 휨 공식. Okay, 휨 공식. Let's change the color to the different one, the blue one. And then we want to define the so-called section modulus. The section modulus in 우리말 it is called 단면 계수. And then we'd like to investigate the shear stress in beams of different shapes of shear stress. And then after that, and this is for the basic information regarding, regarding the force, internal forces and internal stresses. So after that, so rather than talking about just ordinary beams, we'd like to talk about built-up beams. Okay? in 우리말 조립법. And then after that, we'd like to talk about the application of principle of superposition, 중첩의 원리. For the beam problem, combination of beam problems and the actual problems. And then after that, we'd like to talk about the effect of holes and the other abrupt changes in the cross sections to the stress measure. So up to this point, we always talk about how to calculate the stress field. So make sure that the calculation of stress field represents just nominal stress, 공칭응력, okay? 공칭응력. The 공칭응력 doesn't mean the exact stress value. The exact stress value is influenced by many different things. For example, if you have any holes, as we discussed, in the subject of stress concentration factor, we always have so-called 응력 집중, okay, stress concentration. Then once after we calculated the nominal stress, and we need to multiply the stress concentration factor 응력 집중 계수 to the nominal stress 공칭 응력 to calculate the actual the stress value. Okay, so this is very important. Once we have any sudden geometric change, we need to consider the stress concentration factor. Okay, stress concentration factor. Okay. So because the outline was short, that's why I didn't make a break before we talk about moment and curvature. So now let's revisit my diagram. So how to tackle a mechanical problem is always same. So we have to use the force equilibrium and then displacement comparability. These two conditions are given at structure scale. And also the same relation can be, similar relation can be, devised on the material point scale. That is the relation between the stress and the strain. So we call that, relation is constitutive equations or the constitutive laws or the material laws. The reason that we call it this is laws. Law means 법이잖아요, 법. 예? 그러니까 그냥 그렇다고 하는 거죠. So typically we measure this, we determine this relation by experiment. That's why we call it laws. Okay, the law, material law between stress and strain. Then actually, because force equilibrium, there is certain one-to-one relation between the force and stress, especially if you have a hardening behavior. If you have any softening, the relation cannot be one-to-one. So even for the same the force value, we may have the different stress values, but that is that is not in the scope of our class in the mechanics of materials. That's why I don't want to talk about in detail. But if you have any softening, 변형열화, softening, then the behavior becomes more complicated. But as long as we are talking about the linear elasticity behavior, the relation between the force and stress is 1-to-1, okay, 1-to-1. And then here is the strain. Strain is connected to displacement using the displacement comparability. This is called 적합 조건, okay. And this is 평형 조건. 하영이 지금 왔군. 좀 빨리빨리 당겨라. Okay? Okay, so here let's talk about the flow analysis. 하영이 대답 안 하냐? Okay, we can start our analysis from the force equilibrium and then finish our analysis at the point of displacement comparability. But so as I told you, if you have strain softening, then the relation becomes, becomes not the functional relation. That's why we'd better always start from the displacement comparability. That provide more general point of view. Let's start from the displacement comparability, and then we'd like to finish our analysis at the point of force equilibrium. Okay, so now let's talk about deformation of beam. So look, so I want to talk about displacement comparability. To discuss displacement comparability, I have to determine how to describe the deformation. So now let's look at the deformation of beam carefully. So as a simple example, so we have a cantilever here. Then let's say so we applied a force P at the end of this beam, and this is my coordinate. So here this is my x-axis and this is my y-axis. Okay, let me change the direction of my iPad, otherwise it is not easy to grip my iPad. All right, so before, as I told you, before any analysis, we have to introduce a coordinate, longitudinal axis. So we call it x, and then the lateral direction we put the y-axis to measure the displacement. So make sure that although the beam is given a thick red color here, but make sure that we are talking about the representative axis, which means it doesn't have any thickness of the beam. So we are talking about just a line. It doesn't have any height. Okay. So here first we want to measure the displacements of a beam at any point along its axis. Axis means the y-axis, isn't it, right? Along the longitudinal axis from its original position. What I mean, from this original position. Where is the original position? This is the original position. Okay. And then we'd like to measure this displacement. Okay, so the displacement in the lateral direction, especially in beam problem, we call it deflection. Okay, deflection. in 우리말 처짐. Okay, typically the horizontal axis represents the original position of the beam, while the vertical axis represents the lateral deflection of the beam, as I told you. Okay, say if you have a loading here, according to my choice of coordinate system, and then we have certain deformation. So according to my map, so first I'd like to define the displacement field. So we'd like to measure the displacement by the deflection, okay, by the deflection. So let's say what's going to happen if you have a deflection. So if you have a deflection, we have certain deflection, then let's imagine a small segment here. So if you have a small segment, look, small segment, and the size is dx. And then before this deflection, so we have two straight plane, okay, here and here. So I have two straight plane. And then if you have a deflection, then let's consider if you have positive deflection, then this segment will deform like this. So if you look at the bottom fiber is stretched, and the top fiber of the beam cross section is compressed, isn't it right? Initially, so we had two parallel planes, but after deformation, these two parallel planes are inclined toward each other, isn't it right? Inclined toward each other. So if you measure the angle between these two planes, so we may have non-zero angle here, isn't it? So we may have non-zero angle. So initially, the angles are same. So in these lines, we are talking about that stuff. So I want to imagine the M1 and M2 here. So if the cross section is deformed, then we may have so-called center of curvature. Center of curvature is 곡률 중심. And then from the center of curvature to the point of beam, we have a radius of curvature, 곡률 반경. 곡률 반경, okay? And then here the angle between normals. So normals here, then we can measure the angle by d theta. And then differential segment length is measured by ds, the length ds, okay? So now let's try to calculate the curvature. So if the condition is small deformation, not a large deformation, so we can measure the curvature. The definition of curvature is 1 over the curvature, the center radius of curvature rho. So this is the curvature. Now by the definition, curvature is the derivative of angle change. Angle change with respect to x-coordinate. This is the curvature. Okay? Then, for example, here at this center, this is the support of cantilever. Then there's no angle change, isn't it, right? Because at the support of fixed support, that there's no angle change. Any lateral displacement, any rotations is prohibited. Okay, prohibited at that point. So that's why the curvature it should be equal to 0 here too. But if you look at here, then this is the free surface. Okay, although the angle change is non-zero, but there's no change of angle. Angle is still the same because this is free end. So still the curvature is equal to 0 at these 2 points. So, okay, as a special case, in the case of pure bending beams, if you have bending moment the same, then in this case the curvature is constant, and then but if the moment value changes, then curvature changes too. Well, in the case of non-uniform bending beams, we have some functional values of curvature in the direction of x-axis. So now let's define the sign convention for the curvature. So if you understand this the choice of the Cartesian coordinate system, typically we choose the curvature in this direction is positive, okay? That's why we'd like to follow the same conventional sign convention for the sign convention of the curvature. So we'd like to choose the curvature is positive if the deformation of beam is bent concave upward. Okay, if this is this curvature, it follows this curvature, we'd like call this is positive curvature. I'm gonna call this is positive. If it's negative, the bend concave downward, then we'd like call this negative curvature. If it deforms like this, then this is negative. Is it clear? Do you have any questions? No? All right, so then let's move to next step. So we just talked about here, we just talked about the displacement. Okay, so next step, we just about the displacement. Next, what's the next step? Next step, so we need to talk about the strain here. Okay, strain. Then how to calculate the strain using the comparability. Should be comparable, should be comparable using the comparability condition. So let's move the part where the calculation of the strain. So now we understand that. So we wanna measure the deformation of beam segment using the curvature. Okay, so we have the deflection. If you have deflection for beam problem, it is the deformation is characterized by the curvature. Okay, this is the point that we want. So this is the center of curvature, and this is the radius of curvature, and this is the angle. Okay, this is angle. So we want to focus on this fiber. We want to focus on this fiber. So before this deformation, the length of this fiber is equal to dx before deformation, isn't it? So before deformation, it is straight, and then because of the curvature, because of this non-zero curvature, and then the fiber changes its length. Okay, that's what you want to calculate. So how to calculate the strain? The definition of strain is what? Definition of strain is given by, so we already defined when we talked about the axial members. So we defined that the strain is given by the derivative of displacement with respect to x coordinate, isn't it? Right? That's what we discussed. So here, if you change it to the differential form, then it becomes the change of displacement and then the change of the coordinate, isn't it, right? So approximately. So that's why this is the calculation of the strain. Strain in the x direction is given by initial length dx, and then the numerator part, we need to consider change of displacement. The change of displacement, so we need to consider the length change. After deformation, the length is measured by the L1, and the initial length is L. Okay, so let's check one by one. So the length after deformation is, how do you calculate the length? So if it is small deformation, we can calculate the length using the radian relation, isn't it? So we need to consider the angle d theta, and then we need to check the distance L. Then here, this distance can be easily calculated by the length times angle d theta. Okay. So now the d theta is already given here. Okay, already given in our consideration. Then we need to measure the length to these red, fibers. So the fiber to the reference axis, we already know that this is the radius of curvature, and then its position is defined from the reference axis by what? By y coordinate, isn't it? So that's why the distance from the radius of curvature to the red fiber is equal to the radius of curvature minus y coordinate to the position of the red fibers. And then it should be multiplied by angle d theta to calculate the length of the red fiber, isn't it? So here, so let's look at the definition of the angle. The angle is what? The angle d theta is equal to, where is it? D theta is d theta is, okay, look. So from the radius of curvature, so if you extend this consideration up to here, the original length is dx, isn't it, right? So d theta times the radius of curvature is equal to dx. So if you move rho to the radius of curvature to the right hand side, So we can obtain dx over d rho for d theta. Okay. So if you expand this equation, so instead of d theta, we have dx and rho. So rho is cancelled. So we have only dx here. That's why. Okay. So now let's calculate the strain here. Let's plug L1 to this place. So we just move the expression into here. The original length is equal to dx and divided by dx. So what is the common factor in the numerator and denominator? In the numerator and denominator, we have as a common factor, we have dx. The dx is cancelled. If dx is cancelled and this guy also cancels, so finally we have the strain is equal to minus of the coordinate divided by the radius of curvature. So again, for the small deformation, the 1 over radius of curvature is equal to the curvature, just the curvature, isn't it? So my strain is given in very simple form, the minus times the curvature times the y coordinate. Okay. So look, here we discussed the nature of curvature already. My curvature is equal to 1 of the radius. Okay. That's what. So finally, we were able to calculate the strain for given measure of deformation. And then for the position where we want to calculate strain, and then we were able to the strain. So according to this, so let's check the characteristics of this equation even more here. So I want to put the new node. So if I do that, so according to my calculation, my strain is equal in the x direction is equal to minus curvature times the y coordinate. So make sure the curvature is representative value, isn't it, right? So representative. What? To the cross section. To the section. So to the section, the curvature is the same because this curvature is measured at the point of the neutral axis. Okay. Which is representative to the cross section, and then it depends on the y coordinate, which means so at the position of neutral axis, my strain for beam problem, my strain is equal to 0, and then it is a linear with respect to y coordinate. My strain, this is my strain distribution. Okay, my strain distribution is linear. Is it clear? My strain distribution is linear. That's the meaning of this equation. So my strain distribution is straight. Okay, straight. So here I'd like to take 10 minutes break before we talk about more on the beam problems.